Thank you for joining us for our talk from AWS Deep Learning Containers to scaling Amazon Rufus on Trainium. My name is Nguyen, and I'm joined by Adam Zhao. Today we'll talk about open source, AWS contribution to the open source community, and Adam will talk about secrets of Amazon Rufus, highly scalable and a performant LLM inference cluster. So this is yet another chart depicting how open weight model closing the gap with frontier model. And this is showing exactly that it takes about 7 months before you can expect an open weight model running on a single consumer GPU matching today's frontier model, which is pretty astounding if you think about it. So at AWS and Amazon, we've done a number of contributions to the open source community across many different levels of the stack. Most notably in 2021, we started our partnership with Meta and PyTorch on several initiatives such as Torch Serve, Torch Elastic, and the Amazon S3 plugin. And today, very excited to also support the VLLM project by providing some cloud credits for the CI, and also a number of contributions across Amazon and AWS, not only on GPU performance, but also leading the Nguyen support in VLLM. And also, we've made VLLM part of the deep learning container so that it's easy for anyone to get started using VLLM on AWS. So in order to support this open source innovation engine, AWS provides a modular and a flexible stack composed of building blocks across compute, storage, and network with open interfaces. So this allows you to build frameworks for the constantly evolving LLM landscape for different accelerators and optionality in mind. So it might be worthwhile to pause and take a look at the current paradigm shift we're going through and see some of these implications at the infrastructure level. So I heard across several talks, and including the keynote, that we are shifting from pre-training to inference and post-training. And within inference itself, we are also seeing a shift between input-heavy token to output-heavy token, right? At the beginning of the LLM era, RAG and stuffing the context window for summarizations and translation, and then evolving to chatbot, multi-turn conversation, to today's reasoning models, powering those agents and deep research type of use case, right? So shifting from input-heavy to output-heavy, and those reasoning models changing the pattern of compute and memory consumption, right? With a bigger emphasis on memory consumption. And so, in order to work around those memory limitations, there has been many different innovations across several frameworks and across several use cases, right? Page attention from VLLM, to how to train a model using multi-query attention, MQA and GQA, and maybe quantizations and all the different hardware supporting different numerics and data type, to different strategies on how to offload your KV cache across different memory tier or storage tier. And finally, disaggregated architecture. So as you may know, in a transformer model, there are two phases or two stages. There is the prefill, which is known to be compute bound, and then the decoding, which is known to be memory bound. And so, initially, when you have those two different stages on the same host, when you run the decoding phase, very often your GPU sits idle, right? And so there was a need to decouple those two different stages. And so now you see VLLM and SGLang supporting this type of architecture, also known as disaggregated architecture. So by allowing to allocate resources for prefill and allocating more flops or high compute GPUs, and then allocating more memory optimized for decoding, it allows you to really scale those stages independently and more efficiently. And also you have, you need another protocol to transfer the KV cache across those different clusters. Another trend is the rise of mixture of expert, or MOEs. Inherently, MOEs provide 2 to 4x better cost performance. So when you train a model, you only need to train 2 out of the 8 experts, or update the weights of 2 out of 8 experts. At the same time, when you run inference, you only need to activate 25% of the weight, right? There's, however, a trade-off. When you deploy those MOEs model, there's a bigger memory footprint and a more complex deployment in nature. And you also may be familiar with the 3D of parallelism, right? Data, tensor, and pipeline parallelism. And they all share similar characteristics in terms of communication patterns, right? They all have symmetric and data volume exchanges between those different nodes. And MOEs breaks those assumptions, right? And so when you do expert parallelism, you need to shard those different experts across different nodes, and each expert needs to communicate to another expert. So this is also known as all-to-all communications. You can also expect a 3 to 6x more communication between those experts compared to dense model, and very hard to predict the volume between those different experts. And so therefore, there is an asymmetric type of volume and communication in nature. So Amazon and AWS provide the elastic fabric adapter to enable those advanced networking patterns, also known as EFA. And so EFA allow you to bypass the OS and allow you to do RDMA, or direct GPU to GPU communication, right? And EFA relies on libfabric. Libfabric is an open source library to allow you to author those advanced communication patterns. Libfabric is also integrated with other standards and different protocols, such as OpenMPI or NVIDIA, NICO, NVSHMEM, or NIXL. So it's not just on the networking layer, but you can also use EFA on the storage layer. So you can use EFA to read from storage directly to GPU and allow for better throughput and to saturate your GPU more quickly. So we touch on networking, storage, and finally compute. So VLLM, great platform to run over 100 model architecture across different accelerators, right? We touch on how the prefill and decoding are becoming separate and require different hardware characteristics. And so now you can allocate GPU, Trainium Inferentia, AMD, and other accelerators to better serve those tasks specifically and get a better utilization overall of your resources. And so VLLM allows you to really benefit from the variety of those compute and allow you to build those use cases with optionality in mind as well. We've made the VLLM framework part of the deep learning image and container so that it's very easy for anyone to run or build on top of VLLM on top of AWS, right? So we've encapsulated all the complexity of libraries dependencies, optimize the runtime and different drivers so that you can deploy and be confident that it's going to run VLLM with the best experience. So whether you are innovating at the AI gateway or router using different framework and maybe needing to integrate with different inference engines such as VLLM or SGLang, maybe you need to author those advanced communication patterns using NVIDIA, NIXL, or NICO. Or maybe you want to do KV offloading using LM Cache and Mooncake. Or maybe doing fine-grained GPU orchestration using Kai or Ray. And finally, maybe you want to author those custom kernels using a variety of building blocks on AWS. And so AWS provides all those different building blocks with an open interfaces so that you can evolve as those use cases are evolving. Okay, so Adam is now going to be talking about Amazon Rufus, the shopping assistant, and how they were able to scale to 80,000 Trainium chips during Prime Day.
Thank you, Vi. So my name is Adam, and I'm going to talk about some of the experience that we have within Amazon Rufus and how we built such application to run at Amazon scale. So what is Rufus? It's really a conversational shopping assistant that developed within Amazon that can deal with a bunch of shopping-related tasks. So you can think about as simple as the tasks like asking a factual question specific to a product, or ask this assistant to give you some recommendations on some circumstances that you come up with, like you need help from someone, that you can buy something to fulfill the task. And what we want to do is really to build an AI-powered feature available on Amazon through both mobile app and also Amazon website that can help customers making informed decisions when they're shopping on Amazon. And deals with a wide range of questions that powered by advanced generative AI technologies. And pretty much what we have been doing here with all the people sitting down there, developing all these fancy algorithms and also model innovations, we collectively build this innovative approach to conversational shopping experience that is non-existing before. So at early stage, when we started building an inference stack specifically, or the foundation infrastructure to power the Amazon Rufus feature, we faced a couple challenges. So there are major 4 challenges I want to list here, and we will go through why they are challenging in what sense. So first, you need to understand that we are building an application that's running at Amazon scale, and also it needs to be run reliably. Not something that you can deal with today, but it crashes tomorrow. And the average compute that we need to handle is about 3 million tokens per minute. And you need to serve millions of customers around the globe at that scale with high availability and reliability. And second, you want throughput that to serve multiple, hundreds of customers, but you also want speed. So latency is also important to us because people are very spoiled with the CPU-based load nowadays, that they are very used to responsiveness on these fast applications. But you understand generative AI usually is a bit slow when you compare to CPU-based workload. And you need to really invest heavily to make them running fast. And we want to still honor that the experience for our customers where we want to put that constraint under 1 second so that we can stream back responses to customers as soon as we can, and they're getting instantaneous responsiveness from the application as possible. And third, we want to make sure this business is running with a sustainable cost. And that helps us to ensure that we can continue delivering new features to our customers and make the business sustainable. How do we achieve this is we want to build a scalable inference cluster with low overall cost at Amazon scale. And fourth, I think nowadays the trend is people are still building larger and larger model. Although that activated parameter size is reducing, but you still see 100 billions of parameter size models being developed. And you need to make sure that these models can be loaded into the memory before you can serve them. At one point, you may no longer have an instance that has the total memory that's fitting a single model that we are building here. So we don't want to be bottlenecked by that. And that's very important, that how can we remove this constraint on model size. So the solution we landed is really a combination of the levers that we have and the tools that we have that within Amazon and also from open source community. So we landed a solution to build the multi-node inference cluster with AWS Trainium chips, PyTorch, and also VLM. So there are two very important pillars related requirements that we thought about when we come up with this solution. So on one side, we do have requirements around model performance. So we want to achieve the best speed and also the best throughput. So we want to maximize the compute and also memory utilization to achieve that. On the second side, we also want to build a very robust infrastructure, and also that's easy to transfer to be as flexible as possible to be transferred to dynamic infrastructure options. So what we need is a containerized abstraction of this multi-node topology that can do communications very efficiently and also maintain the consistency across nodes. And we need this infrastructure to be flexible and scalable. And that means that we can port this solution into any infrastructure that we are evolving into and be keep evolving for the next adventures that we have collaboratively. So let's look into a little bit more into the details on the architecture that we have. So this is an oversimplified version. So you can see there are two types of nodes. One is the leader node, one is the follower node. And theoretically, ideally, you really can scale this into tens of dozens of nodes that doesn't have to be just two nodes. But this is just for simplicity here. So you can see that leader node and the follower node, they are almost identical. Leader node is just taking a little bit more responsibility here. So what the leader node does, in addition, is to do the request orchestration. So the leader node leverages VLM for efficient dynamic traffic scheduling for follower nodes to execute. And what it does is to leverage something like continuous batching available from VLM to broadcast the inputs and assign these requests to all these follower nodes that we have, and so that these follower nodes can start executing. And for sure, leader nodes also have compute, because it's also a GPU device, so it can broadcast to itself as well. And when the follower nodes receive those inputs, then they will start execution. So during the input broadcasting, we leverage PyTorch, which is the torch distributed library for the input data broadcasting. And during the actual request processing, there will be a lot of collective communications happening across nodes. And we leverage the Neuron NXDI library, which is the Neuron Distributed Inference library, and also the Elastic Fabric Adapter, which is EFA, to leverage the high bandwidth and the low latency inter-node communication. So which ensures that we can move data around efficiently, and also we can minimize the networking overhead. And in order to achieve the best performance on a certain model and also with the certain infrastructure you have, you tend to always need to do a little bit more fine-tuning. So what we do, in addition to think about what the architecture should be, we also invested a little into the model parallelism strategies. So on one side, we want to maximize the memory bandwidth, which is MBU. On the other side, we want to also maximize the flops utilization, which is MFU. So one stands for the compute, one stands for the memory, and that's exactly what we're talking about here is throughput and latency. And you also need to have a good balance because you're dealing with so many nodes at the same time. You don't want to overload a single node, and that becomes the bottleneck to slow down everything. So you want to minimize the memory pressure on individual nodes when you have such architecture. And we use a hybrid parallel strategy, meaning it's hybrid in the sense of prefill stage and decode stage. They use different strategies here. At the prefill stage, we leverage context parallelism, which basically split the input of the same request into smaller sequences along the context. And then that we can do the parallel computation for the prefill and also attention computations across different nodes. And at the decode stage, we use data parallelism so that we can shard or partition the data or requests along the batch dimension, and we can deal with a subset of the requests across different nodes. So they also help to balance the workload across the nodes. And all these, what we just talked about, we have a very well containerized solution built around it. So it's a nice abstraction that we can port it into a certain infrastructure that's not necessarily built by ourselves, but it can also be leveraged by other customers if they want, with native PyTorch, VLM, and the Neural SDK support. And also it's generalizable to other hardware types. So one important I think I want to echo is if we talk about EFA support with GPUs, but EFA also supports a variety of hardware types, like Trainium and Inference is one example that we built with these solutions within Amazon. And also, we're able to use this solution and scale for the Amazon traffic with EC2 and ECS. These are very scalable and robust services available for the compute and the deployment. We also have these levers that we can leverage to minimize the cross-node latency overhead. So on one side, we do have the flexibility to optimize the node placement. So you can think about when you deal with data center, you want to have the affinity of the nodes located physically closer so that they are physically lower in the network overhead. And on the other hand, we will also leverage EFA again to achieve this low latency by leveraging the high bandwidth and for the cross-node communication. And another thing very important to ensure the robustness and the reliability, availability for a system is you need to have a good telemetry and also monitoring system. And AWS has the CloudWatch service that we also leverage to build that. So it gives us alarms when there's errors happening and gives us good telemetry and visibility into the service. And lastly, we leverage Trainium chips because it has a very good advantage in terms of price performance. It's 30 to 40% better than the comparable GPUs. That's also a public available data that you can search from the Amazon official posts. And there's a link over there, which is an AWS blog post we posted earlier this year, has a little bit more details if you want to learn. And feel free to go there and check that out. Yeah, so just a quick recap. What we mentioned, 4 challenges we faced when we started building the inference infrastructure and stack for Rufus application in Amazon. So we had a challenge in latency, which we call it user perceived latency, because you need to send something meaningful, visible to customers when they feel that you are responsive. And second, you need to make sure that your infrastructure is reliable and scalable, that can support customers as the business grow, and also for certain volume traffic per second or per day, on a daily basis. And third, you want to have the low cost because you want to make sure the business is sustainable, and also you want to make sure that you can continue delivering new features to customers as long as you are running business efficiently. And lastly, you don't want your infrastructure to be a bottleneck on the model innovation. So you want to unblock yourself from deploying any size of the model, and then you're really doing distributing inference with multi-node, and the model can be sharded across multiple nodes and they're running collaboratively. And lastly, I think AWS is really want to innovate together with all you guys and also open source community, and to continue to build and innovate on AWS. And we believe the next breakthrough in AI will come from someone sitting in this room or in this conference. And Fee is here also I think one of the mission that we want to fulfill, which is an ongoing mission, is to give you the building blocks for scalable and performant AI solutions that we can offer from Amazon and make it happen. And there is, I think, on November 3rd, there is another deep dive on MOE meetups with Meta and NVIDIA at AWS Loft, which you can check more details by clicking the link below. And welcome to find us at that booth on November 3rd. Yeah, I think that basically closes my presentation. Thank you.
Thank you.